if you look at the result of the BFS, here is the graph. This is the original graph. And then we are going to see the connected components of S. The connected component of S means we are going to check if the graph starts from A. Okay. So what are the connected components from A? And then if it connects to B, we want to check what are the connected components from B. What are the connected components from C? What are the connected components of D? And so on. Then the property 1 says that the BFS visit all the vertices and edges of GS. If GS are the connected components, then we will visit all the vertices and we visit all the edges. We visit all the edges. And the property number 2, the discovery edges labeled by BFS G, S form a spanning tree. So TS is the spanning tree of GS. So L0, it is a kind of level. Let's say this is L0 or the level 0. Then it has only one vertex. Every connected component from this vertex will be level 1 or L1. Every connected component after this level, it will be level 2 or L2. So for each vertex V in Li, so for every vertex in L0 or L1 or L2, the path of TS from S to V has I edges. So if you look at this one, from A to the level 1, we have I edges. If it is from S to V, it has I edges. If it is the tree, the spanning tree, it has 3. Okay. Then we have 1, 2, 3. So at least you have 1. We have 1. We have 1. And then every path from S to V has at least I edges. From I to V, at least we have 1 edges. Because it is 1. From B to E, you have only 1 edges, but it refers to the I. Okay. If we have L2, then it means from S to E, we have 2 edges, 1 and 2. L1, from A to A, B, we have 1 edges. So that's the meaning by I in this case. The analysis, when we want to set or get. Set means we want to create a particular label. For example, we want to set the node or the vertex as visit. So we set the label. Get the label. It means if we want to know the get W, whether it is unexplored. So we want to check whether it is already explored or unexplored. Then it is get. This set and get, the running time is 01 because only just get and set. Each vertex is labeled twice. The first is unexplored and the second is visited. So it means, yeah, we have only 2 times. And then each label is each edge is labeled twice, whether it is unexplored or discovery or cross. Each vertex is inserted once into a sequence Li. So insert. So when we have a new vertex, then it will be inserted into Li. So the method incident edges is called once for each vertex. Then in the worst case, we say that this is On plus M. N means we have N vertex. And M means we have M edges. So On plus M time provided the graph is represented by the adjacency list structure. So if your data structure is adjacency list structure, then you will get On plus M. And we can recall that the sigma, sorry, this is not S, this is sigma. It's the sigma of V, degree of V equals to 2 multiplied by M. Now, let's look at the comparison. When we can use DFS and when can we use BFS? So both of them, they are good on making the spanning forest. Both of them, they are good on finding the connected components. And both of them, they are also good at finding paths and cycles. But if you want to find the shortest path, usually you will use BFS. And if you're finding the bi-connected components, usually you are going to use DFS. So in the next section, we are going to discuss about the short paths. And if you look at the result, okay, the result of DFS, the spanning tree is going to the deep, okay, we call it this is depth. So after A, we look into B, and then we look into C, yeah, we look into D, we look into E, we can look into F. So we want to find the deep analysis for every of this node. If we look at the BFS, we use breadth. Breadth means after I check A, I'm going to check another level, which is B and C and D. After I check this level, then I will check E and F. So the sequence is a little bit different between depth and breadth. So those sequence make the difference with the applications. If the shortest path, yeah, you will do with the breadth. If you are using the bi-connected components, you are going to use with the depth. And what is the difference between DFS and BFS? If we use the DFS, we call it backends. What is backends? Backends means the ancestor. Ancestor means the parent or the grandparent. W is an ancestor of V in the tree of discovery edges. So if I already visit A, and then I go to B, and then I go to C, and then I go to A. So this is the parent, or we call this is the ancestor. If we use BFS, we have cross edge. So the cross edge of V and W, the W is in the same level as V or in the next level. So if you look at the BFS, B and C and D. So you go to B, from B to C, and you look at the A visit B, A visit C, A visit D. Then we cannot go to C because C already visited. You cannot go to D directly because D already visited. So we call this is W and V, they are in the same level. Or if you already visit E from B, so you cannot visit E from C. So this is not possible. Then it means this is the cross edge. Whether W is in the same level or V, as the in the same level as V or in the next level. So in the next level is this one. So this is in the next level. So this is the things you learn about the graph. You learn about the graph, DFS and BFS. Now let's take a look about the code. So I put the code in the, sorry, I didn't put the code in the PowerPoint. I put the code in the e-class. So you can go to the e-class. Mm. This is the graph example from the book that I refer as your reference. They have the graph section in the chapter 14. Okay. So let's say this is the graph, the class graph, and then you have the vertex. You are going to create the vertex. So what is the vertex? What are the element name? And then you have the hash. It means we want to put into as a key in the dictionary. And we want to get the string. And then we have the edge. It means I'm going to make the connection between one vertex and another vertex. So let's say this is U, this is V. And then we can construct the edge by looking at the U and V. U, let's say this is the origin, and then V, let's say this is the destination, and X is the element. X is the element of the edge. The element can be anything. For example, you can say this is the cost, or you can say this is the distance, and so on. We want to check what is the endpoint. So the endpoint means we have the origin and the destination, U and V. We want to check what is the opposite. The opposite of V means I'm going to check what is the instance of V, and then I want to check what is the destination if V is the self-origin, as it is the origin. And then this is the element, and then hash, and this is the string to represent it into the print format. And then using the graph methods, I think we already learned about the outgoing, incoming. Okay. So what is outgoing? It means from one vertex, we want to see the outgoing or go out from the vertex. Incoming, it means we have the vertex and then it is coming to the vertex. So this is outgoing, out, and this is incoming. And then we want to validate the vertex, whether the vertex is available on the graph, and then check whether it is a directed graph or not. If it is a directed graph, then it means I have a direction for the graph. And then I want to check how many vertex do I have. And then this is the set of vertices. So if I have A, B, C, D, E, and so on. Okay, so these are the set of vertices. And then edge count. So how many edges do I have? And then this is the set of edges. And then let's get the edge. The edge means I know the U, I know the V, and then I want to check is the V and U is connected or not, or if U and V is adjacent or not. And then I can also calculate the degree. So how many edges connected to one vertex? The incident edges means the collection of the outgoing edges in the vertex V. I can insert the vertex, I can insert the edge, and so on. Okay. Now, if you run this, let's say I'm going to make a graph from the edge list structure. So this is the edge list structure. Using the edge list structure, let's set up the default directed equals to false. So the graph, it is directed equals to false. And then V is a set. Now I'm going to add the E0 and E1. And then the vertex is empty. And then let's insert all the vertex into the vertices. And then let E be the collection of E. This is the edges. And then let be the E0 is the source, and let E1 is the destination. And then let E2 be the element. If length of the E is higher than 2, then let's make it null. And then you are going to insert the vertex into the G. So if you look at this one, okay, just let's see. We have Seoul Daejeon. Then it means I have a connection from Seoul to Daejeon. And then Daejeon to Busan. Then I have a connection from Daejeon to Busan. Busan to Daejeon. So it means I have a direction Seoul to Daejeon, Daejeon to Busan, and then Busan to Daejeon, Daejeon to Suwon. So let's say this is another node. I put Suwon. And then Suwon to Seoul. So there is a direction, Suwon to Seoul. So Seoul to Gwangju. Say this is Gwangju. And then we have Gwangju to Suwon. Gwangju to Suwon. So this is the graph. Okay. This is the graph based on this edge. And then this edge, I want to put true. True means this is the direction. Direction, it is true. So I have the direction from Seoul to Gwangju, Gwangju to Suwon, and then Suwon to Seoul. But there is no direction from Seoul to Suwon. Yeah, maybe there is a limitation for the trip. So this is the graph that we can create based on this simple example. What about the other? This is from the book figure 14-3. So I guess this is the same with the Yeah, maybe this is the same with this one. Oh, the same with this one. Maybe I will put the figure 14.3 later. But if you look at this one, this is the HE and then true. Okay. HE and then directed for is false at the default. But if it is true, then it is a directed graph. Then you can see here we have the POS to SFO and then POS to JFK. So I think this is the airport connection, POS to MIA, and then JFK to POS. So there is a direction back from JFK to POS, JFK to DFW, and then JFK to MIA, and then JFK to SFO, and then ORD to DFW, and then ORD to MIA, LX to ORD, LX to ORD, and then DFW to SFO, DFW to SFO, ORD, DFW to ORD, DFW to ORD, DFW to LAX, MIA to DFW, MIA to this one already, MIA to LX. So you can have like this graph. So using this graph, then you can make the graph. Let's say this is the graph of Korea. Oh, sorry, I need to run this. Then I can run this one. So I have a simple example. Then I can know what is the incoming edges. The incoming to Daejeon, it was Seoul and Busan. The incoming to Gwangju, yeah, it was from Seoul. The incoming to Suwon, it was from Daejeon and it was from Gwangju and so on. And then what is the outgoing? So you can check the outgoing. From Daejeon, the outgoing, it goes to Busan, it goes to Suwon. From Gwangju, it goes to Suwon. From Suwon, it goes to Seoul. From Seoul, it goes to Daejeon and Gwangju. From Busan, it goes to Daejeon. Okay. So I can also create this graph, 14-3, and then I can check what is the incoming nodes and what is the outgoing nodes. And then you can also use some kind of element. This is to represent, for example, the distance, or maybe cost. Maybe this is the cost of the flight from San Francisco to Los Angeles, yeah, or anything. So we can get each of the number to represent this node. So from SFO to LAX, let's say this is false. False means there is no direction. Then the cost or the distance between SFO and LAX, the X element from SFO to LAX is 337. And SFO to Boston, POS, it is 2704. Maybe this is the mileage and so on. Then if you have this one, you can use this example. And then again, I can check what is the incoming and what is the outgoing. This is the DFS from the book. So DFS, we have the graph and then we have the U. We want to check what are the discovered edges. At first, I want to check what are the incident edges, and then check the opposite. If V is not discovered, then discover V equals to E, and then go back to the DFS. So I can construct a path U, V, discovered, and then I'm going to check for every of the path. If it is discovered, then let's append into the path. And yeah, you can check this one. While walk is not in U, then E is discovered. And check what is the opposite of walk. And then if there is a parent, then let append the parent into the path. So walk now equals to the parent. And then we can reorient the path from U to V. So this is the DFS complete. For every U in all vertices, let's check. If U is not in the forest, then forest U equals to none. And let's do the DFS. So DFS is this one. So this is the DFS. I'm going to use the graph Korea that we created before. And then, yeah, we can have the DFS. This is the spanning tree from the graph Korea before. So if I use the incoming, yeah, you can use the incoming item, and then you can check, okay, from the graph one. From the graph two, you can also check the result. So this is the code for the breadth first search. So this is from the book. This is what I explained before, okay, from the BFS. And then you can just run. Now we can get the BFS from the graph Korea. So this is the BFS from the graph Korea. And then this is from the graph one. And this is from the graph two. Now, when you do with your team project, okay, I ask you to create a small example. But how can you do the experiment with big data? So I give you example how to create your data randomly. Okay. So this is an example in the graph. Now let's suppose I'm going to make a random graph. I start the n with 10 and then m with 30 nodes. Sorry, n is 10 nodes and m is 30 edges. So I'm going to make a random graph. N and m will be random from this number of nodes and edges. So I can make the file name as the test edge list. So I'm going to write into this file about the edges. Yeah, so you can have this one, test edge list. If you want to open, so this is the edges. For the graph one, let's add 0 and 8. For the graph one, let's add 0 and 3. For the graph one, let's add 0 and 9, and so on. Then we have the random graph with 10 nodes and 30 edges. And now let's put this random graph into a list. For example, yeah, you want to use list as your data structure. Then after you append this one, you can get, let's suppose I converted the graph not into the list, but I'm using tuple. So this is the tuple. Then let's create the random graph using the edge list structure. The edge list structure is from the previous section. Now I'm going to create another graph with n equals to 100 and m equals to 300. So let's say I put this as LL100. Then again, I create another random graph with 1000 of nodes and 3000 of edges. I put it into the LL1000. Now let's check the runtime performance. The last time we already did this one. Okay. Now let's check the runtime performance. Let's say I'm using the DFS. So I'm going to check the graph Korea, the graph random 1, the graph random 2, the graph random 3, and the graph random 4. So these are the generated graphs. And then I will do runtime graph Korea, runtime graph random 1, graph random 2, graph random 3. So you can get the time. So after you get the time, okay, let's say this is another graph which is higher, 10,000 and 30,000 nodes and edges. So after you have this one, let's do the runtime. And then let's check for every of this into the list. So I know the list will be the T1, T2, T3, T4, T5. And then I want to compare the time performance for each of the data. After I have the DFS, now I want to run with the BFS. The BFS also the same using the graph Korea random 1, random 0, 2, random 0, 3, random 0, 4. And then I use the S1, S2, S3, S4, S5. And then check. If the data is 5, how many times do I need to run? If the data is 10, if the data is 100, if the data is 1000, and if the data is 10,000. Then you can get this data for the DFS. You can have the data and the time. So this is the graph, time performance of DFS. If it is very small, yeah, the time performance is small. If the data is 10,000, the data performance is 0.05 something. And then I can also compare between DFS and BFS. So if you look at this one, the red color is the DFS and the blue color is BFS. In this case, even though they have the same peak O, n plus m, but in terms of the running time, it seems that BFS is lower, or the BFS is faster than DFS. Okay, so you can explain this one in your team project presentation, and you can give the conclusion. For example, in the time performance, BFS is slightly higher than DFS. I think it depends on your performance, and in this case, DFS is higher than BFS, but maybe because of the random time. And then you can specify what are the computers that you use, whether you are using your laptop or you are using a desktop. And please mention your specification about your computer. Where do you use for your experiment? Okay, I think that's all for the graph. I think the time is not that enough. Then